But what exactly is a benzene ring and why is it like toxic to us?
I
We'll
will
probably
get
go
to
over this
that.
later. Okay, yeah.
I will get to that. It's an excellent question. So benzene, we're not really going to be talking about benzene today, but I will mention it in the slides here. Today, we're going to be focusing on the simplest molecules as far as organic chemistry goes, and that is hydrocarbons, named hydrocarbons because got hydrogen, they got carbon. And so we'll be talking about substitutions, talking about linear hydrocarbons, branched hydrocarbons, and how to name them. So, where is my annotate? Oh, there we go. So, yeah, you think of the word organic, and I don't know, people freak out like, oh my God, organic chemistry, or people who aren't chemists will just think, well, organic probably means, something that's been grown without the presence of herbicides and pesticides. And so it's organic, man. But in chemistry, it's really, really rather simple. What is organic? It just means a molecule that has a carbon atom in it. That's it. That makes it organic. And we've been dealing with certain carbon compounds so far, but basically they've been in the form of, carbon monoxide, like simple molecules, carbon monoxide, carbon dioxide, some polyatomic anions like carbonate, that sort of thing. But one of the cool things about carbon is that it is really super flexible. I'll talk about that in a minute. It can form just a huge variety of molecules that have like really interesting chemical properties. And so that's why not only is there like a whole branch of chemistry called organic chemistry, but then it's broken down even further, where people specialize in just, carbon anions, carbon cations, carbon involved in enzymatic processes, carbon involved in biochemistry, huge array of different carbon compounds. And so we'll be learning about a lot of them in the coming weeks. So just the study of carbon compounds, all it is. Don't have to freak out. We're just, all the molecules we're going to be dealing with from now on are going to have carbon in them. It is a chemical diversity, as it says, unrivaled by any other chemical element. Of all the molecules on Earth, probably well over half of them have carbon in them. So that really doesn't, no other element can do that, like not even hydrogen or oxygen. And hydrogen and oxygen have rather relatively limited ways of putting them together, whereas carbon, you could make, like I said, millions of different molecules. So why is it so diverse? Well, carbon atoms make pretty strong bonds with other carbon atoms. So when you burn something with carbon in it, it burns at a fairly high temperature because it takes a lot of energy to break those bonds. And we'll find out the more that carbon is bonded, the greater the energy is in those bonds, and the greater the heat would be produced when they're broken. Carbon atoms also strongly bond with other atoms, other elements. Carbon atoms have just a slightly higher than average electronegativity, around 2.5. And so it can form nonpolar bonds, it can form polar bonds, it can form, extremely polar, not so polar. There's a wide range of polarities of bonds that carbon can make too. And carbon makes 4 bonds. For instance, hydrogen can only make 1. Oxygen can only make 2. Nitrogen can only make 3. Carbon can make 4. And so basically it makes like the most bonds of any of the typical elements that we've been looking at, any of the simple elements we've been looking at so far. So it makes the most, and it makes them in a wide variety of strengths, both weak and strong, polar and non-polar. So carbon can do a lot of different things. So all living things, we all have organic compounds in us. Most organic chemicals are covalent. So as I mentioned, carbon makes non-polar bonds, it makes polar bonds. Very rarely will it make ionic bonds. It does make carbide, it can make carbide ions. In fact, there's a whole company named after that, Union Carbide, the chemical company. And so you can get things like tungsten carbide blades on a cutting tool or on a drill bit, and they're incredibly hard. I mean, tungsten's already like the hardest, not the hardest metal, but very, very hard indeed. You add a carbide ion to it, and it's even harder. So if you look in a hardware store, you probably will see different tools bragging that they're made with carbide. So, but they're very, very rare. Most of the chemicals that we'll be dealing with are covalent, polar and non-polar. So the simplest ones are the hydrocarbons. As I mentioned, they just have carbon and hydrogen. That's it. And so the backbone of these molecules will be carbons linked together, then with hydrogens attached, making up the rest of the bonds. Now, we would call that an alkane. An alkane, another word for alkane, is saturated hydrocarbon. And what we mean by saturated, there aren't any double or triple bonds between carbons. So if you have a carbon-carbon double bond, those can be broken and replaced with bonds to other atoms. Like you could break this bond and then replace it with hydrogens bonded to each carbon. In fact, you've probably heard of the term saturated and unsaturated fats. Anyone know what a saturated fat is? Based on what we just talked about.
One carbon bond linked with a hydrogen.
Yeah, all single bonds. All the carbons have single bonds. And when the carbons have single bonds, when they all have single bonds, they have, and we'll see this in a little while, they all have a very similar pattern. It kind of looks like this, of carbon atoms bonded together. And then they can just lay on top of each other with a lot of London dispersion forces and become a solid at room temperature. So if you have a saturated fats like in butter, butter has a lot of saturated fat in it. So all carbon-carbon single bonds, and it is a solid at room temperature. On the other hand, oils, which have very similar compounds to butter, are unsaturated, and in some instances, polyunsaturated. That means that they have carbon-carbon double bonds. And they can form all kinds of, they have these sort of bent structures to them that aren't quite as regular. They'll look like this. So they don't stack up on each other quite as well as saturated molecules do. And so they have less London dispersion force because of the shape. Their shapes don't allow them to make as much contact with the other molecules. And so if there's less London dispersion force, that means they don't interact quite as strongly, and they are liquids at room temperature.
Is that the reason why saturated fats, because of, I guess, it just having single bonds, it's more tightly packed, I guess, and then
Exactly.
unsaturated is loosely packed?
Exactly. Yeah, exactly. That's a great way of putting it. You can pack saturated molecules together because they're all similar shapes. Unsaturated, or this would be polyunsaturated, poly just meaning there's more than two double bonds. They kink into all kinds of interesting shapes, and so they don't fit together quite as well. And so then you get fewer London dispersion forces and less stacking, less packing on top of each other. So an alkene has one or more of these double bonds like this. And so we would say it's unsaturated because it doesn't have the maximum number of hydrogen atoms that it could, considering the number of carbon molecules. And an alkyne has at least one triple bond. And a triple bond, we would draw it like that, with a line above and a line below, meaning that the carbon, here's a carbon, here's one, here's one, here's one, and these two carbons have a triple bond between them. So they wouldn't have any hydrogens attached to each other, because they'd have three bonds to each other and then a single bond to the other carbons on each side. So there'd be lots of room for extra hydrogens to be added to this particular molecule. It also means that it burns at a very high temperature. One of the most basic alkyne is acetylene, and you've probably heard of acetylene. That's acetylene there. Acetylene is used for melting steel. That's how hot it burns, because this triple bond has a lot of energy in it. It takes a lot of energy to break that. And so the amount of energy it takes to break that means you need to have a really high heat to break it. And so it burns at a very high temperature.
What about trans fats?
Excuse me?
Trans fats, is there any kind of
Oh yeah, I'll talk. Actually, we'll talk a lot about that in the next chapter, because in the next chapter we're going to be talking about alkenes.
Okay.
And so we'll be talking about cis and trans. And basically what that means is when you have carbon-carbon double bond, if you have substituents on the same side, like if I have a chlorine here and a chlorine there, we'll say they're on the same side of the double bond, and we'll say they're in cis. If the substituents are on opposite sides, like that, then we say they're in trans, because they're on opposite sides of the double bond. So trans fats just means that they have substituents on opposite sides of the double bond. But we'll talk a lot more about that in the next chapter. So there's lots of ways to represent hydrocarbons. We can draw them in a bunch of different ways to show what they look like. And so this is the simplest way. That's just the straight up molecular formula. That's just the only information with that is how many carbons, how many hydrogens. That's it. It doesn't tell you anything about how they're put together. So you don't really know how it's assembled. Now, a condensed structure sort of breaks down what's happening at each carbon. So this tells you that the first carbon has 3 hydrogens attached, the second one has 2, the third one has 3. And then the Lewis structure basically gives you the whole thing. So this gives you the least information, the first one, and then this gives you the most. And we'll see that there's another way that chemists use of representing these, because there's such huge molecules that you basically want a simple way to draw them without having to draw every single bond in them. And we call that the skeletal structure.
And you want us to know all 4 of these, correct?
Yeah. So let's do an example here. So Lewis structures. So the first one, so basically when you're drawing a Lewis structure for hydrocarbons, you find what's the length of the carbon chain. So if we look at this first one, we can see that there's 1, 2, 3, 4. That is butane, also called N-butane. N just because it's all in a row. So we just go 1, 2, 3, 4, because we know they're all the carbons are connected to each other. And we also can tell just by looking at this particular way it's written, we can see how many hydrogens are attached to each one. Although we should be able to figure that out because each carbon makes how many bonds?
4.
4. Always makes 4. So I have carbon 1, 2, 3, 4. And you can see carbon 1 only makes a single bond, so it has room for 3 hydrogens. Carbon 2 is making 2 bonds, so it has room for 2 hydrogens. And the same with carbon 3. And then carbon 4 is making only 1 bond, so it has room for 4 hydrogens. So that would be the Lewis structure simple Lewis structure for butane. Now the next one, I've got 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 carbons in a row for this one. So 1, 2, 3, 4, 5, 6, 7, 8. So I look and see how many hydrogens are attached to each one. So the first one has 3. So 1, 2, 3. Now look what happens between carbon 2 and carbon 3.
Double bond.
Double bond. Yes, indeed, Dylan. That was Dylan, right?
Yeah.
All right. Yeah, there's a double bond there. So we put another bond. We can't put it here because this carbon already has 4 bonds. And you can see that the double bond appears between number 2 and number 3. So then everybody else just gets hydrogens. So since carbon 2 here and carbon 3, how many bonds does carbon 2 and 3 showing right now? How many bonds are carbon 2 and 3 making at this point?
Alkene.
Like 3.
Yeah, they're making 3 each. So they only have room for 1 hydrogen. The rest of them in the middle of the chain have room for 2. Until we get to the end. And if at the end of these, if you just want to do H3, that's fine with me. Because we're going to be drawing a lot of these. And so if you just want to put CH3 at the end of these molecules, that's fine, rather than putting each one of them around. So that would be acceptable. So anyone know what this would be called? It's got 8 carbons. So what would be the prefix for 8?
Octa.
Oct. Now, is it an octane, an octene, or an
Octene.
octine?
Octane.
Octene, that's octene.
And that's because of the double bond, right?
That's because of the double bond. And we also say where the double bond is.
Is
And
it
it starts at carbon 2. So we would call that 2-octene. That would mean that it's got a double bond starting at 2. And so 2-octene. Excellent. So this is a structure we're going to get used to drawing because it gives us a lot of information, and we can draw large structures fairly easily. It's called a skeletal structure, or basically a bare bones. Whoops, let me go back. A bare bones structure. Now, what it doesn't show hydrogens. So we don't see any hydrogens here that are bound to carbon. We don't see any carbon-hydrogen bonds. They're assumed. So we just assume if we don't see a hydrogen there, and like for instance, this carbon right here is bond has 3 bonds, a double bond on one side and a single bond on the other. So we assume it's also bonded to a hydrogen. If it's bonded to something other than a hydrogen, we mark it. Like for instance, this carbon is bound to an oxygen, so we point that out. This carbon is double bonded to an oxygen, so we point that out. And then this carbon has an OH, a hydroxyl group, not hydroxide, hydroxyl group, so we include that. But other than that, we don't include carbon hydrogen bonds. So we just assume they're there. So that frees up a lot of space. So we can put a lot more information there without having to draw all those carbon hydrogen bonds, because there's going to be a ton of carbon hydrogen bonds in hydrocarbons. So look, so that is naproxen. And we're going to be talking a lot about these or aromatic rings. And we'll be talking a lot about those in subsequent chapters, because a lot of really interesting, those are the benzene rings you were asking about. So we'll be talking a lot about those, because there's a lot of really interesting chemistry involved with those. So, like I said, skeletal structures only show bonds except carbon hydrogen bonds. Everything else is shown. So carbon-carbon bonds are represented with just a line. So a line is supposed to be a carbon at one end and a carbon at the other end. That's what's to be assumed. So here's our molecular formula. What's that particular molecule? Got 3 carbons.
Propane.
What is it?
Propane.
Propane, that's right. Methane, ethane, propane. So that's the simplest way of representing it. Or we can show basically what each carbon, how many hydrogens it's bonded to and what order they're in. We can show the full Lewis structure, or we can give the very simplest way of showing it, which is the skeletal structure. And it doesn't get any simpler than this. That's it. So what this represents is that this is a carbon at the end, this is a carbon here, and that's another carbon at the end. And there's no double bonds, and everything else is hydrogen. So that's as simple as it gets. If we were in the lab playing with models, we would see that this is what it actually would look like in 3-dimensional space. And it's kind of fun to build those because it gives you a good idea. Like all the stuff we were learning about shapes, we can see them in action here, because you can see what is the shape around each of the carbons in this molecule. If you go back to your, if you remember your shape part, the shape chapter.
Not the trigonal?
What is it?
Trigonal?
No. Trigonal means 3. So they'd be trigonal if there were only 3 bonds, but there's 4. So it's each one is making 4 bonds. The ones on the end are making bonds with 1 carbon and 3 hydrogens. And the one in the middle is making a bond with 2 carbons and 2 hydrogens. So they're all making 4. So what do we call the shape with 4 bonds in it?
Tetrahedral.
It's tetrahedral, that's right. And notice that each one of those are tetrahedral. If you look at the shape, that's tetrahedral, that's tetrahedral, that's tetrahedral. So that gives you like the most information on the shape. And it also explains why we call it, why we make that particular structure, because you can see that that's in 3 dimensions. That's what the carbon does too. So if you have a long carbon structure, it goes like this, up, up, down, up, down, up, down. So you can see that If we add another carbon, it would be up here, then another one would be down there. So that's why we make the structure look like that.